Did you do that, the cube root of 25, was that the last thing in your notes?
Yes.
Okay. So today's piece, we're going to talk about differentials, and then I'm going to give you guys some time to work so you can ask questions over anything from Friday if you need to. Guess I should do my notes. All right. When we see this, a triangle x, triangle y, that means the change in x and the change in y. Those are the actual change in x and y on a curve. So if I have some curve and I'm looking from 2 points, okay, the actual amount the x changes and the y changes. That's my change in x and change in y. When we see a differential, that is denoted with dy, and that is our approximation to the change in y. If you think about it, if we were using a tangent line here. Change in y is the actual amount. dy would be like the amount y went up on the line, not on the curve. So if we're using the line to approximate the curve, dy is the amount y increased on our line. Change in y is the amount it increased on the curve. What do you notice about the change in x? Dx is the change in x on the line, but dx is going to be the same as the change in x. Okay, the change in x on the curve and the change in x on the line are the same. To think about how we find this, dy dx is the same thing as the derivative f prime of x. So dy, our approximation to the change in y, is f prime of x dx. So let's look at a problem and try to figure out exactly what I'm talking about here. Compare the values of change in y and dy. If my function is x cubed plus x squared minus 2x plus 1, and for part A, x changes from 2 to 2.05. All right. So 2 and 2.05, these are just 2 points. They're the x values. You are going to need a calculator today. We can't do, well, we could. We are not going to take the time to do all these calculations in our heads. All right, if I put a 2 into this function, so if I put in a 2 for all my x's, I get out 9. Now let's put 2.05 in. And I get 9.717625. So the actual change in y, the amount y changed on the curve, you just subtract those. You do your ending point minus your beginning point. It started at 2, it ended at 2.05. So I start with the 2.05 y value, subtract the y value when the x was 2, and I get my change in y to be 0.717625. Could change in y be negative? Yeah, if it were going down. So that's why we don't necessarily do the bigger minus the smallest. We do the ending minus the beginning. All right. That's my change in y. I want to compare that to dy. So we know, think about our differentials from Friday. Dy dx, if I did the derivative of this, that's the same thing as f prime. So that would give us 3x squared plus 2x minus 2. So my actual dy is 3x squared plus 2x minus 2 times dx. This is the differential. It's how we could approximate our change in y. Our x value, when you're doing it this way, it's our starting point. So my x was 2. My dx is how x changed. What happened to my x? It went from 2, it increased by, so my dx, my change in x is 0.05. If it went down, it would be a negative. So if I plug that in, I get 0.7. So my actual change in y was 0.717625. If I'm using my differential to approximate it, I would have had 0.7. So fairly close. I want you guys to try B, where it changes from 2 to 2.01. I want you to find both the change in y and dy for that scenario. So you plugged 2 and 2.01 in. So our actual change in y, if we subtract those y values, ending minus beginning, we get 0.140701. Did everybody get the change in y? Okay, so dy, our approximation, is same setup as up here, your derivative, times the change in x. Our x still started at 2, it ended at 2.01, so the dx is 0.01. So if we plug that in, we get 0.14. Any questions there? Then the last part of the question just wanted you to compare those. So both times it was pretty close. Which one was closer? This one was off by 0.017. This one was off by 0.0007. So which one is closer? B. So our conclusion, we could really say that our differential is getting really close to the actual change in y when the change in x is small. And that really shouldn't come as a surprise, right? We know that a line, the tangent line, is a decent approximation for the curve if you're really, really close to your x value. The further away you get, the less accurate it is. So if we're really, really close to our original x value, our differential is a really close approximation. The further away we get, the less accurate it will be. All right, one situation where these differentials comes up is in calculating the maximum error of something. Okay, if you think about a manufacturing process, you know, if you're making something, there are multiple parts that each little part gets made and put together to make a bigger item, right? Is every single part going to come out exactly the same? No, there's going to be some variation. So you have to know, like, how far off can this part be so that my final object will still work, right? And if I am measuring this, let's say I'm trying to design like a tire. Okay, well, how far off would this, if I take this measurement, how much is that going to change the overall area of my final tire? Or how much will it change the volume of my final tire? What's acceptable? And so that's a situation where we see this. We're not going to go super in depth here. We're just going to look at a couple basic examples and just kind of get a feel for that. But here is one such example. So the radius of a sphere was measured and found to be 21 centimeters with a possible error in measurement of at most 5/100th of a centimeter. So my radius is 21. The error in my radius, that's like my differential, my dr, is 0.05. Sorry, do you want me to give you a second to write? I forgot I didn't print them for you. So we know our radius and we know the error in our radius. What's the maximum error in using this value of the radius to compute the volume of the sphere? So we are looking for the error in our volume. So dV is really what we need to find here. If we are talking about volume of a sphere, I guess I should add that to our list up here, shouldn't I? So we have to do the derivative to get our area. You can call this dV/dr when you do the derivative if you want. Since we're talking about differentials, if you just want to go ahead and call it dV and put a dr over here, it's 100% what you guys prefer. Do you guys have a preference? Okay, so is it okay if I just call this dV and then over here I'm going to put a dr on the end? So 4/3 pi, that just represents the coefficient, so 3 comes down, 3 times 4/3 would just be a 4 pi r, subtract 1 from the power, so 4 pi r squared. So now we can plug in our stuff. dV is 4 pi times our radius is 21 squared times our dr, which was 0.05. And this is going to be ugly enough. Let's go ahead and just multiply out the pi as well. So the maximum error in volume is around 277 cubic centimeters. That's the most my volume measurement might be off. So if this were something and I thought, well, that is too much error, that won't work, I would have to go back and make sure my radius measurement was more accurate. I would have to lower the DR in order to make this more accurate. Okay. Questions on that? So what I want you to do now is work on that handout that was posted on Classroom Friday. Check yourself, ask questions, especially since I wasn't here. If there's something that we're having trouble with, let me know.